Okay, so starting in on our lecture here on datums, projections, and coordinate systems, I'm going to start with a couple of maybe the world of the abstracts, talking about georeferencing in general, and then the size and the shape of the Earth. But then we'll really get into basically defining these three different parts of the discussion, if you will, so that we can understand how to make sure that our data overlays one on top of the other are different data layers. So the theme here is tying your GIS data to a location in the real world. So I use this term georeferencing in a general term, sort of an overarching term. We'll learn later how to georeference data. We'll actually take scanned maps that are sitting in image space, sort of floating out there, and actually georeference them using the georeferencing tool in ArcMap. But in this case, we're using georeferencing sort of in a overarching term that describes ways that we can tie locations to some known place on the surface of the Earth. So place names, for example, or meets and bounds, indicating where places are sort of in a relative matter. Maybe you're indicating where the edge of your property is, and you're delineating that maybe in an older way of saying 50 paces north of the old oak tree, east to the old fire hydrant, and then there's a big boulder 20 paces to the west of that, etc., etc., using this kind of general relative location to describe where places are on the surface of the Earth. Postal addresses are another good way to determine that. For example, 7201 Rossville Boulevard, Baltimore, Maryland 21237, using an address and zip code to indicate where CCBC Essex is located. As an example, there's no other place in the world that has those parameters, and so that's a way to uniquely indicate where we are on the surface of the Earth. Linear reference systems are a good way to indicate where you are with transportation, for example. A classic example of that is just the mile marker system on our highways. We're able to tell emergency services or a tow truck to come help us out if we know what mile marker we're located. So for example, Interstate 95 north between mile markers 104 and 105 indicates to them a general location of where you are, and help or services can be brought to you. So again, indicating how we can locate ourselves on the surface of the Earth. Similar to meets and bounds, we use what are called cadastrals. A lot of times when you're looking at parcel data or property data for an area, who owns what property, it's known as cadastral data. And so very similar to meets and bounds, sort of delineating, say, the longitude, latitude measurements of the corners of a property. And that's how a lot of our polygon GIS layers indicate who owns what at the local and state level. GPS, obviously ubiquitous throughout our lives. We're using it for turn-by-turn directions and various other reasons, for collecting data that winds up within a GIS, and so we can locate ourselves on the surface of the Earth using longitude and latitude coordinates or some other type of coordinate system. Speaking of coordinate systems, longitude and latitude, these are really the focus for this lecture and for this demonstration. What we call metric georeferences. Metric meaning that we're making some sort of a measurement from some known location to locate ourselves within a given data set, or locate ourselves somewhere on the surface of the Earth. So really this is just a listing of the various different ways you can try to identify a unique location on the surface of the Earth, but really we're focusing here because this is what's most important in terms of our GIS data. And as I mentioned, we're going to kind of start with a little bit of the abstract here, kind of thinking about the size and the shape of the Earth. A lot of times we think it's just a big sphere floating in outer space, but of course, if we take this dashed line and indicate that that's a perfect circle or a perfectly spherical type shape, the Earth is actually not perfectly spherical. It's flattened at the poles, so you can see the sort of the light purple violet kind of color here, this bulging inwards towards the equator, but then at the equator itself we've got this bulging outwards. And of course, it's centrifugal force. The Earth is spinning on its axis through the poles, and we're going to get this bulging at the equator, and that creates an equatorial and polar circumference that has a slight difference. In this case, we're showing it at about 42 miles. Maybe negligible, but it's definitely measurable. So when we talk about the shape and size of the Earth, the shape of the Earth is really an oblate ellipsoid. We'll talk about ellipsoids here in just a minute. But oblateness is a flattening, so we're getting these flattening, kind of squishing at the poles and bulging out towards the equator. And so we use spheroids and ellipsoids to try to estimate, as closely approximate the shape of the Earth. The shape of the Earth is extremely exaggerated in this example here, just a shot from one of my other textbooks, where we see the continents. Here's the Himalayas, Indian subcontinent, Asia, Saudi Arabia, Africa, Australia, Southeast Asia, throughout here, and we can see our deep ocean basins, and of course the continents rising above sea level. That's an extreme exaggeration of the shape of the Earth. But when we talk about the shape of the Earth, we name it, or we call it, the geoid, and this is kind of the technical definition: an equipotential surface of the Earth's gravity field which best fits global mean sea level. Wow, kind of a long and drawn out way to describe this. So what the heck does that mean? Well, if we can imagine sea level just kind of sitting still and not fluctuating with the tides, and no wind, and we have this nice perfectly flat ocean, which is rarely, if ever, the reality, we extend that line from the surface of the oceans through the continents onto the other sides and connecting it to oceans on the other side. We can create this kind of optimal kind of surface that is the shape of the Earth, without the fluctuations of continents rising above sea level or the ocean basins dropping below sea level. Okay, so what does that mean? Well, basically the geoid is what we call typically the shape of the Earth. And so we use mathematical objects like ellipsoids and spheroids to mimic that, so that we can have it within our digital space in a GIS, but we also use these mathematical representations of the Earth to do mapping, and have done so for a long time. So when we look at what a spheroid or an ellipsoid is, this mathematical surface created by rotating an ellipse, a flat two-dimensional object, about its shorter axis, axis, in this case Earth's polar axis. So Earth's polar axis is shorter than its equatorial axis. So if you take this imaginary ellipse and rotate it, you're creating this three-dimensional object that we use to try to fit to the geoid. And of course the geoid is the actual shape of the Earth. So we're trying to use math, or a mathematical object, to approximate this extremely irregular object that is the Earth. The first person credited with creating mathematically calculating this figure, or this estimated shape of the Earth, was Alexander Ross Clark. So make note there that I've underscored the 1866 spheroid, the Clark 1866 spheroid. And note that date, 1866, because that's going to come into play when we start talking about datums right here in this next section. So moving forward, we have to define what a datum is, and we'll do that in just a second, but we need to address the fact that Clark's 1866 spheroid is extremely outdated, and more recent spheroids like GRS 80, which stands for Geodetic Reference System 1980, or the more recent and familiar WGS 1984, which you may remember from one of our earlier assignments, is the ellipsoid that we use for the coordinate system that we defined for our earthquake assignment. So these are more up-to-date and more accurate because they use modern technologies, satellite technologies. The field of geodesy really is focused on measuring the shape and size of the Earth to extremely accurate measurements. So we use WGS 1984 typically, and as time goes on, tectonic shifts occur, gravitational fields change, the Earth is going to change, and of course more updated spheroids are going to become available to be used for our GIS data. And so we'll see this referred to as we continue on our discussion. So let's define what a datum is. A datum is a reference point or points from which other measurements or references can be taken or can be made. Really good examples of this are monuments and benchmarks. Maybe you've been out in the world and you've seen these things stamped into a concrete block or into some sidewalk location, a place that doesn't move. And so measurements, northings and eastings, can be taken off of that location. And so we've got a couple of different datums that we use here in North America, specifically in the United States. that reference the previously discussed ellipsoids. So datums are basically our starting points for being able to measure or make measurements with our GIS data. And so commonly used datums in the United States, or in North America in this case, is what we call NAD27, or North American Datum 1927. It's based on that Clark 1866 spheroid, and so it's using the estimated size and shape of the Earth developed by Clark back then in 1866 to make measurements here in North America. Notice that the origin is at the surface at Meads Ranch, Kansas, and that's significant because that's the geometric center of the United States at the surface. But when we look at the more recent North American datum of 1983, it used the GRS 1980 spheroid, and the origin is based on the center of the Earth. So if we think about longitude and latitude, for example, they are angular measurements made out to the surface from the center of the Earth. If we're measuring longitude east and west of the prime meridian, for example, at the 0 degrees longitude line through the Greenwich prime meridian, that's an angular measurement from the center of the Earth out to the surface. Likewise, with latitude, we're making an angular measurement from the center of the Earth, a line shot out to the equator, and then of course a latitudinal measurement north or south of the equator on up to 90 degrees north or south of that line, of that reference line being the equator, and of course the poles being a point location where lines of longitude converge. So with these measurements based on the center of the Earth, as we use datums that are closer to, say, more of a local, more local location, for example, here in Maryland, we use North American datum 1983. We can be measuring in feet or meters, but the datum, the origin point, is based off of the knowledge that we have of where that origin is based on longitude and latitude. If we were measuring from a point location like NAD27 used back at Meads Ranch, Kansas, there is potential inaccuracies there for making measurements with our GIS data. So a lot of what you're going to use, at least in this class, and potentially with a lot of other data that you're using throughout the United States, would potentially most likely be in North American Datum 1983. There's still a lot of data out there in NAD27, but that can easily be converted from 27 to 1983. So just showing a map here of where Meads Ranch, Kansas is. And again, if you can imagine, the United States is a fairly large country. And so as we move away from Meads Ranch, Kansas, let's say we have a system for Utah or for Nevada that has an origin point here in the lower left-hand corner, that point being established by measuring from locations based on Meads Ranch, Kansas, are going to be a little less accurate. If we're measuring that location point, that starting point for the Nevada coordinate system, if we know the longitude and latitude, again, which is based on the center of the Earth, we can then convert that measurement to 0, 0, being the origin for Nevada, and any measurement we make in feet or meters, for example, north and east of that origin, it's going to be much more locally accurate. Now I'm indicating Nevada here. That's a very large state, and there's actually multiple coordinate zones that are used in Nevada. If we look at Maryland, for example, Maryland is a state that only has one state plane coordinate system, and we'll talk about state plane coordinate systems here in just a moment. But our origin kind of sits down here somewhere in Virginia, West Virginia area, and this is our 0, 0 point for making measurements in the northing and easting direction, all of our coordinates being in the positive. So that origin point, that datum, is based on, in 1983, based on the center of the Earth, versus 27, which was based on this less accurate Meads Ranch, Kansas. And of course that's, again, being the geometric center of the lower 48, was the thinking behind establishing that as the original datum. We're going to move on into projections now, and when you start talking about projections, you're really talking about taking this curved, irregular surface of the Earth and taking it and putting it onto a flat surface. So I'll kind of bring up all of these talking points here all at once. You're going to practice projections in Chapter 13, where you get to work with making 3 different maps in 3 different data frames of Alaska, the lower 48, and Hawaii, which are in 3 different latitudinal zones. When we deal with projections, this is what I like to call the squash the orange peel analogy. So if we hollow out the yummy, delicious part of the orange, take it all out, and we're just left with half of an orange peel, you take that orange peel and squash it onto a flat surface, like a computer screen, or onto a map, or onto a table, a chalkboard, a whiteboard. It's going to tear. All right, so that's the point we're making here. There's going to be some sort of tearing, and for you to, if you imagine that orange peel sort of being the surface of a map, you're going to have to fill that in, and so that tearing is going to cause some sort of distortion. And so that's what projecting does when you take the Earth's irregular curved surface and you project it onto a flat map. You create distortions to some aspect of that map, whether that's distance, shape, area, or direction measured on that map. So I've got a couple of examples of projections here. One that's more familiar might be a conic projection. If you imagine, say, taking the entire Earth or a globe and putting a cylinder around it, maybe an imaginary cylinder or even a paper cylinder, and having that cylinder only touch, say, here at the equator. If you were to put a little light on in the middle and kind of turn that light on, it would project the shadow of these lines of longitude and latitude onto the paper, and you can imagine it projecting all the bodies of water and the continents as well. And you would unfurl that cylinder, and you would wind up with this flat map. And of course, this is an example of a Mercator projection, which we'll see here in just a few minutes. The classic example of how it distorts. But you can even see here in this example that the poles, which normally in reality converge, these lines of longitude all converge up towards the poles. Here we get tearing, we get ripping, we get pulling apart of these places that in actuality in real life really converge in this sort of spherically shaped object that is Earth that we live on. So we use different types of projections to try to maximize for what we're mapping. So for example, if we're mapping a high latitude environment, say around the Arctic, we may want to use this planar projection, which puts the point of tangency of this imaginary piece of paper right here at the North Pole. So the most accurate measurements really are going to be around here, and as you move further and further out to the edges, you're going to wind up with more distortion and less accurate measurements depending on what it is that you're trying to measure. When we talk about state plane coordinate systems, which we will hear in just a minute, they tend to use a conic projection because that's ultimately better or optimizes for mid-latitude locations. So here in the United States, most of the country is within the mid-latitude. So again, if you can imagine that sort of piece of paper or an imaginary cone placed over top of the Earth, and of course this standard parallel being the point of tangency where that cone touches, you unfurl that and you get this sort of funny shaped piece of paper, this cone that has been opened up. That line of tangency is going to be the most accurate location. So when we're talking about specific systems for measuring coordinates by state, say by Maryland, Florida, California, we're going to have different systems that use different conic projections to maximize for local accuracy. I like to use this classic example of how Mercator projections distort. We see Greenland here and we see Africa here, two bodies of land that are very large but not exactly the same size. In fact, Greenland is significantly smaller compared to Africa, but on a Mercator projection, we're talking about a landmass that is significantly smaller and is horribly distorted here on this location, or on this type of map, excuse me. So here at the equatorial latitudes, we're going to see probably the most accurate measurements, whereas as you move further and further north, we really start to distort. And you can kind of see this sort of flattening of the north boundary of the United States. I'm actually going to go backwards here in my slides, and if you look at a conic projection, you still kind of get that closer to reality kind of curvature to the map when you use a conic projection versus a Mercator projection, which is a cylindrical projection that really distorts. And so a conic projection would actually be much more curved and maximized for these types of latitudes. The high latitudes in this case really get sacrificed, and of course looking at Antarctica, there's a large landmass, but what this map indicates is that it's much larger than it really is in reality. So of course a globe is going to be our closest approximation of the size and shape of the Earth, or at least the closest model that we can effectively use to model the planet that we live on. let's talk about coordinate systems here for just a second. I've mentioned coordinate systems throughout the discussion, and a lot of times coordinate systems, projections, datums, they're used interchangeably. I do it, I'm guilty of it, you'll be guilty of it too. Remember the distinction that we're making, and that's really the point to this lecture. Understanding what a datum is, understanding what a projection is, understanding what a coordinate system is. But once you start getting into it, a lot of times people sort of mush these terms together. So really want to make that distinction and understanding what we mean when we say something like a datum versus a projection versus a coordinate system. We have several different types of coordinate systems, and if we look here, very simply, we're looking at an example of a Cartesian coordinate system. So we're going to have an origin. So we could imagine this 0, 0 point being our datum, all right? Because a datum is that reference point that we're going to make measurements off of. So in this case, we're looking at this location, location 7, 3. So 7 units in the x direction and 3 units in the y direction. So this is a very basic example, but if you can imagine longitude and latitude being a metric that we use to make those angular measurements from the center of the Earth, this would be our 0, 0 location, which in reality is out in the Gulf of Guinea off of the coast of Africa. And this y axis indicates our prime meridian, or 0 degrees east and west, and then this indicates the equator, 0 degrees north and south. So we would measure in degrees rather than, say, cells like we're measuring in this example. So when we talk about what coordinate systems are, they're used to determine locations on a planar surface, in a two-dimensional surface using an x and a y axis. Now we have several different types of coordinate systems that we'll talk about. And there are lots that are used, and we've already mentioned longitude and latitude. Notice that I put in parentheses a geographic coordinate system. When we're talking about longitude and latitude, when we're measuring, making measurements on our maps, either in degrees, minutes, and seconds, or whether it's decimal degrees, which is the types of coordinates that we use for mapping our points, say for our Chapter 18 exercise for the typhoon in the Philippines, or the XY coordinates that we pulled off of the IRIS seismic monitor for the earthquake exercise. Those coordinates were all in decimal degrees. So instead of saying 93 degrees, 20 minutes, and 5 seconds west of the prime meridian, we might say 90 point some degrees in the negative direction. So that's going to be west of the prime meridian. So that's what we call a geographic coordinate system. And so we use this for world or national type levels of mapping. There are projected coordinate systems, so I've mentioned state plane coordinates, which can be measured in feet or meters or in other units, but typically feet or meters are the ones that we gravitate towards and use. And these are projected coordinate systems, which means that they use some sort of a projection. When they're state plane coordinate systems like the Maryland state plane coordinate system or the Nevada state plane coordinate system, they use a conic projection typically to maximize for that local accuracy at the latitudes, whichever the state is located. Another example is the universal transverse Mercator projection. This uses meters, and it divides the Earth. If you can imagine a circle, it's obviously got 360 degrees, and so it divides up the Earth into 60 equal zones of 6 degrees of longitude. And so when you're talking about universal transverse Mercator, you need to understand what zone you're working in. For example, Maryland straddles zone 17 and 18. And you also have to indicate what hemisphere you're in. And it uses a starting line of measured at 500,000 meters down the middle of the zone. So if you can imagine a zone of longitude 6 degrees wide, the center line is going to be the 500,000 mark. So anything to the west of that line is going to drop in number from 500,000. Anything to the east of that line is going to be measured above 500,000. In the northern hemisphere, it lists the equator as the 0 line location and measures it in meters north of the equator. If you look at the southern hemisphere, it measures 10 million meters to the south of the equator, and so that all numbers basically in a UTM coordinate system, a projected coordinate system, you can see that it's a Mercator projection. So it's using that type of projection to take the curved surface and project it onto a flat surface. It's measuring it in meters from those reference coordinates that I just mentioned. You could very easily Google Universal Transverse Mercator or UTM coordinate system to see an example of this. But again, it is a system that divides the Earth into these 60 equal zones of 6 degrees of longitude, and then uses those 0 or 10 million or 500,000 meter locations as the reference point or the reference lines, for measuring coordinates in the positive, so that there are no negative coordinates within any of those different zones. The point really here is just to list the different types of coordinate systems that you could potentially see. There are lots of different ones out there. These are some of the more common ones used today. And when you move on to the demonstration video, you'll see me talk about each of these different examples. And so hopefully that will minimize some of the confusion from potentially from talking about these things sort of in a lecture kind of situation. So it helps to see this, helps to look at it in a demo, and so that's what I encourage you to do now, is move on to the demo and see this in action in ArcGIS. When you're done seeing that demo, you can go ahead and practice doing some projections, changing projections within Chapter 13.